Hello, this is my math stats final project presentation. So given the current situation that we are in, I thought it might be appropriate for me to do some analysis on COVID-19 data. So the COVID-19 data that I got was from two different sources. One is from covidtracking.com and one is from GHU GitHub repository. And here's a little summary of the data and some visualizations. You can see that the data includes several columns like province/state, country, confirmed cases, deaths, and recovered. And here's just two samples of histograms of these data. And like I said, we can also like plotting the cumulative cases from each region. I should mention that for this project, we are only focusing on the confirmed cases column from the data. The reason behind it will be clear when we actually do the analysis. Okay, so moving on to the actual analysis of the data. Our intuition is that, well, actually people often say this, that the growth of say the infectious population is exponential. So what does it mean, right? So our intuition is actually backed by a scientific paper where it says during the early stage of an outbreak, the number of infectious individuals in the population is actually exponentially related to time, in this case, number of days. So what we actually want to do, the question that we want to answer is, well, the paper says early stage, so how many days can we use to actually fit the linear regression model? So essentially, this is hypothesis testing. So for example, we can do something like take maybe the Wuhan data, the first 30 days. We say the null hypothesis says that they are linear related for the first 30 days, and the alternative hypothesis says otherwise. So we want to test how strongly two variables relate to each other. We can use the correlation coefficients, and this correlation coefficients ranges from -1 to 1. And the more it approaches to 0, the less convinced about their linearity. And plugging in the numbers of Wuhan, we got 0.94. And using the critical values of 95%, it basically works like a p-value. So in this case, 0.94 is a lot larger than the 95% critical value. So there is little evidence against null hypothesis, which means we can actually use the first 30 days data to fit our linear regression model. So here is the actual fit. What we want to calculate is beta 1, which is the slope of our linear model. So when you have beta 1, you can just calculate R naught by dividing beta 1 by gamma. And gamma is actually the infectious period. And this number 7 is widely accepted by a lot of literatures. I cite them here. So here are some graph after fitting the data. You can see the data fits, the model fits the data pretty well. And it gives us very reasonable R naught to 2.3 and something like that. And here is, okay, so the R naught that we calculated in this section is just one number, right? So it tells you how many cases can emerge from one case of infection in your population, but they're just one number. When you want to answer the questions of when you want to reopen the economy, when you can resume to normal life, you really have to see this in a time varying way, because maybe during the early 30 days, okay, the R naught is this number, but as time goes on, the number of infections goes down, the R naught might goes down as well, but we don't know that. So say for the first day you have some belief, about what the distribution of R naught is, right? But after you have seen k cases on that day, the distribution of R naught for your next day is probably going to be affected. So say I got a large number of k seen on day one. So that probably will affect my belief of what R naught will be distributed on the next day. So putting in mathematical terms, this is just a base rule, but putting in mathematical terms, we can just say that the posterior that we get from day one, that is the distribution of R naught after we have seen the first day's data. And we can apply that to our second day's posterior calculation by using the posterior of first day as the prior for the second day. So we can iteratively updating our prior like this. And there is one missing element, and there are actually two missing elements from our calculation here. One is the likelihood. It really should be intuitive, because when you want to model the number of arrivals given a certain time period, it should be a Poisson distribution. And the prior selections, well, for this project, I just used a flat prior, and I assume that the R naught from 1 to 4 are equally likely. So we got all the elements that we need. I just calculate the posterior for New York and California, and they look like this. So every day is a distribution. And we also need to calculate the, so we have the distribution, but we want a number, which is R naught from each day. So what I did was using the method of maximum A posterior estimation to calculate R naught. These are just numbers that you can see from the peak of these distributions, and they look like this. So as time varies, as time goes by, infectious individual goes down, and the R naught reasonably goes down as well. So from this project, I really learned that the real world data is very noisy and it's very hard to deal with. I had to do a lot of smoothing before I could get the Bayesian model to work well. And there are actually some states that still don't work well with the Bayesian updating model. So if I had more time, I would definitely figure out what's actually causing the problem. Okay, so thank you very much for watching.